All right, so today we're actually starting what's probably, I think, a brand new concept to you, which is what's called a logarithm. Logarithm is basically just the inverse of an exponential function. But they can be a little confusing because it is kind of a weird new thing. So our goal today is I can write and interpret a logarithmic function. All right. So this starts off with a kind of a rationale of why logs exist. So earthquakes says earthquakes make seismic waves through the ground. The equation y equals 10 to the x relates the height or the amplitude in microns of a seismic wave. And then y is let me re-say that. So it relates the height of an amplitude in microns of a seismic wave y to the power or magnitude x of the ground shaking it can cause. So the y value is the size of the wave. So literally what happens in an earthquake is the ground starts to shake and it creates the ground waves, like a water wave or something like that, except it's ground. And so these measurements here, these amplitudes are how many microns the height of one of these waves is. So 100 micron height of the wave versus a 10,000 micron height of the wave. And microns are really, really tiny unit of measurement. But when we're talking ground, when the ground is moving, if the ground moves this much, that's a whole lot of ground movement, causes a lot of damage, obviously. So these numbers are, if you've ever heard when people use the Richter scale, that's these numbers. When they say, oh, it was a magnitude 2 earthquake, or it was a 6 on the Richter scale, those directly correlate to how large the ground waves were. Okay. Now, here's the issue about this. So it says, Taylor and Chen used different methods to find the magnitude of the earthquake with amplitude 5,500. You'll notice here you have 2, 3, 4, and they each have a corresponding value. And you probably notice a pretty similar pattern there. Basically, each time it goes up by a factor of 10. This goes times 10, that goes by times 10. So they're asking, what would the corresponding value be right here? So there's two schools of logic here, especially if you didn't know the function. If you didn't know the function and you're looking at this table, Taylor looks at it and says that 5,500 is halfway in between here and here, right? Because there's 9,000 numbers in between there. Half of 9,000 would be 4,500. So it's up 4,500, up 4,500. So she's looking at it linearly. And so she says, yeah, this would be 3.5 right here. And if you don't know anything about this graph, you don't know anything about how this works, that might make sense to you. But if I just count up, what did this amount go up by? What did this amount go up by? That would make me think this is 3.5. Now, that's also kind of ignoring what's going on right here. But she's definitely the one that makes the error here. And then we have Chen, who knows the equation is the 10 to the x. At least he recognizes it because he's like, yeah, 10 squared is 100. 10 to the third is 1,000. 10 to the fourth is 10,000. So he's like, yep, that's the function that's modeled here. So what he does is he checks this out. He does a little guess and check method. And he does 10 to the 3.5, just typing it in a calculator. He's like, well, let's see if I can figure out what this would be. That's 3,100. So that's not high enough. So he just keeps going up until he finds the number, just a little guess and check style. And he finds that about 3.74 gives him about the right answer. So he's able to figure out what should go here, which is approximately 3.74. Okay. Now, is this a huge difference? No, not really, but they are definitely different. 3.5 is different than 3.74. Okay. And so if we look at the couple questions here, it says, what is the magnitude of an earthquake with amplitude of 100,000? So if the amplitude was 100,000, obviously that's just adding another zero, is going to tick this up by 1. So it would have 5 would be the magnitude. Okay. You also know that because 10 to the 5th is 100,000. All right. Critique their work. We kind of already did this. So basically we talked about how Taylor's is wrong because she's using a linear approach. He's using an exponential approach. And we know this is exponential, not linear. That's basically the big problem here. Describe how to express the exact value of the desired magnitude. So the thing you run into here is you have 10 to the x equal to some number. We had the one we wanted to figure out, which was 5,500. And he kind of just had to guess and check because he didn't know what to do. And you don't either. At this point, you're about to learn to, but you don't know how to cancel this out. You've never seen it before. At least you never learned it in any math class we've had so far. So, most things where you have an x, there's an opposite operation. For example, this is not the problem, but if you had 10 times x equals 5,500, you'd be like, oh, the opposite of multiplying is dividing. So I divide both sides by 10 and I solve it that way. Okay, this isn't multiplication, so we don't do that. So we need to be like, well, if I have 10 to the x power, what can I do to get rid of this 10? What's the move for that? And the answer is it's a logarithm. So that's what we're going to learn about here moving forward. So we'll learn about what that looks like on the next page. All right, so let's just solve these equations. So 2x equals 8. That's easy. You've done that type of equation. Probably actually done that specific equation like 20 times. I don't know. Divide both sides by 2, and you're like, yep, x is 4. Easy peasy. Opposite operations are key there, right? 2 times x, so you divide by 2 to get rid of the 2. 2 to the x equals 8. You don't know the opposite operation. You don't know how that works yet. So you would actually basically have to go guess and check at this point. You'd be like, well, what's 2 squared? 2 squared would be 2 times 2, which is 4. So no. What's 2 to the third? You're like, yeah, that's 8. So in this case, x is, not 8, x is 3. And that's really all we know at that point. So this is why logarithms need to exist, because not every problem is this easy. Not every problem would you want to guess and check either. Like imagine if this was some awful decimal, that's going to take you forever to figure out by guess and check, okay? So what exists is what's called the logarithm. And it is defined this way. It says logarithm base b of x is defined as follows. So log base b of x equal to y. That's our base log equation. And that is exactly equivalent, or you can say this or you can write this, if b to the y equals x, okay? So anytime you have this style of equation like we did here, we can rewrite it using the logarithm function. And the logarithm function is just like a sine or a cosine or or tangent or any of these functions that exist that basically mathematicians just figured out all of the answers, made a giant table, and downloaded or uploaded that table into a program. So like our calculator is programmed to do logs because every log is just programmed in there. Like you can do log of any number, you can do the inverse of any number because they've been entered into there. So when this says rewrite the logarithmic form of this, so this is like what we've got here. So let's reorder it just so it's kind of written exactly like that one. And so the rule is you have by equals x. So the base, the exponent, and what we call the argument, okay? So what we do here is to write it in log form, the b is always the base. So whatever the number being raised to is a little subscript here. So log base 8. The x is the what part it's equal to, which in this case is y, is going to be equal to whatever the exponent is, in this case x. So again, when you read a log problem, when you read the way this is written, we'll talk about how to enter it in the calculator, that kind of stuff eventually, is this saying that the base to this power equals this. So again, what are these parts? You have the base, you have the exponent or the power, and the special name for this one, which is probably a new term to use, is called the argument. Okay. So what does the power equal? The name for that, again, this part is called the argument. So just to put these kind of things all into perspective, you got your base and your exponent. So the same terms, base, exponent, argument, base, exponent, argument. That's where they go when you write it as a logarithm. All right. Now, again, you don't really know what to do with this yet, but you notice there is a button for it on your calculator, and that's exactly what it is. So because of this, we have what we call two different forms. You have exponential form, which is what we had right here. 8 to the x equals y is the exponential form to the problem. You have this, which is the logarithmic form. Log base 8 of y is x. These are equivalent. So these are just two different ways of writing the same thing. Just like how you can write a linear equation in point-slope form or slope-intercept form or whatever, these are equivalent forms of the same thing, okay? So if you know this is true, you can write this. If you know this is true, you can write that. That's the idea. All right, so let's flip ahead here. And today's base focus is just writing the log and exponential form. So actually not going to do any solving today at all. So it says, what is the logarithmic form of this? So remember, you're going to do log of the base, which is 3, of the argument equal to the power. That's the logarithmic form. Okay, when they give you, it says, what's the exponential form of the logarithmic form? Base to this power, so 10 to the third, equals the argument, 1,000. Which also makes sense. Like when you're writing this, you can look at that and be like, oh yeah, that's right, because 10 to the third power is 1,000. So that's the relationship between the three numbers that you have in a log and the three numbers that you have in a power or an exponential. Okay. All right, another one of the same thing. Pause it for a sec, see if you can write those. Okay, logarithmic form of this. So log base 7 of 343 equals 3. All right, and then log to exponential form, 4 to the second equals 16. And so that's all you're going to see today. You're going to probably kind of fly through these. They're pretty easy. And we're going to start getting to how do you type and solve these going forward. Actually, sorry about that. I lied. We are going to solve these. My mistake. I was thinking we were doing examples 2 and 3. Or sorry, 1 and 2, but we're on 1 through 3 because these actually aren't too bad at all. All right, my bad. So example 3, we are going to look at solving basically mentally, not by calculating yet, because that piece is a little bit different. So solving these mentally, when they say, what's the value of these log expressions? When they say, what is log base 5 of 125? You have to look at that and say, all right, so this is going to equal something. This is going to say, like, it equals X. So 5 to what power would give us 125? So now you have to think of this and say, all right, well, that would be 5 to the third, because 5 times 5 times 5 would give me 125. And so that's how they figure out this answer. So this is log base 1/4 equal to 16. So we got to figure out what power would that be. So I think of this as 1/4 to what power would give us 16. Now you might be thinking, like, well, if I squared this, I'd get 1/16. So how do I get it to be a 16? Well, it'd have to be a -2. Because if you have 1/4 to the -2 power, that's going to be 4 to the second power because of how negative powers work, which is going to be then 16. All right, here, this is 3 to what power equals 0? Fun fact. Fun fact, if you remember we have asymptotes on exponential functions at 0. This can't happen. This has no solution. There's no way you can ever get 0. And then here, so what I would probably look at this here is we could say this is, 2 to the 8th is some number, but we actually can kind of get around not having to do that, because think about it. This is going to say 2 to the x is equal to 2 to the 8th, which then becomes super obvious that x is just 8. All right, so these are using the rule and kind of mentally being able to work out the problem. We're not doing any calculations yet. We're not using the calculator, other than if you need to, do power to figure out what it would equal out. That's fine with me, but we're not using the log function in the calculator yet. So here's another one. This is saying 3 to what power equals 1/81. So 3 to the 4th would give you 81. So 3 to the -4th is going to give you 1/81. Whoops, not 18. So in this case, we'd have -4. Here we'd have 7 to the x equals -7. So how can we just get it to be the opposite sign? Don't think that can happen, right? So we just think about some stuff here. So one way you could think about solving this is if I have 7 to the x, and I want to see, does this ever equal -7? If we graph this, it's here. Never gets down here. Remember, these only output positive numbers? So this is another one I would look at, and I'd say this is definitely a no solution. We can't get a negative out of this. And then here, 5 to the x equals 5 to the 9th. It's as easy as they get. X is 9. All right. So we're going to try these out on the OTI today, and we'll see how it goes for you. And we'll learn some calculator stuff the next day.